Hello everyone. Okay, in this video I'm going to show demonstration of the resultant force calculation, and it's from your homework problem. Okay, let's see. And this one. Okay, is a resultant force calculation. Okay, and I make a demonstration. Well, that's 3.392 and 393. Okay, and this problem is, okay, there is a beam on the support. Okay, looks like the pin support here, and there's a roller support. Okay, but this support is not relevant to this problem because the problem wants you to replace the loading by a single resultant force and space by where the force acts. And these two are almost the same problem, but 192 is okay. Determine the position of resultant force, and the reference point is A, and this 93 is determining the resultant force, and the reference point is at B. Okay, so actually the same problem, but different reference point. Okay, so they just want to do a simplification on. Yeah, looks like it's very similar to simplification, but just the final result is just the final resultant force by the least external simply very simple external loading. So the resultant force calculation, first of all, okay, we have to calculate the magnitude of resultant force. That's the first step, and I think it's very relative easy. Okay, relative easy. Okay, first of all, let's find out, okay, what's the resultant force? Okay, resultant force. Okay, how to say it? Okay, like I find resultant force. Okay, simplification. Okay, what is the resultant force? Okay, what the resultant force? Okay, okay, when do the resultant force, because this problem, okay, it's very nice. The nice of this problem is we can this is like a 2D problem. So in 2D problem, when we calculate resultant force, you only have to use just the summation, the resultant force in X component and resultant force of a Y component. Okay, so resultant force X component, okay, equal to what? Okay, let's look at this. Okay, so we have X component force here. This force 450 Newton. Yeah, it had X component. Okay, but it act at this point, so it has this. Yeah, I think I should write here. You have this. We can decompose this force in the X direction and Y direction. Okay, vector decomposition. And here is 60 degrees. So and yes, that means here is 60 degree. Okay, 60 degrees, so it's cosine 60 degrees, 450 and times cosine 60 degree. Okay, and it's point to the right. Point to the right, so it's positive. Okay, let me check. Okay, okay, point to the right there. That's good. Okay, so X component, okay, this has X component and the 300 Newton force, there's only Y component, okay, no X component, so we can ignore it. And this force 700 Newton here is acting at this point, so, yeah, we have X component here, Y component here, and this is 700 cosine, sorry, this is 30 degree here, so this should be 30 degrees here. So it's 700 times sine 30 degree. Right? Sine 30 degree. Okay. And the direction, because it's pointing to the left, so we have put negative sign in front of it. So I think that's all the X component of resultant force. And using your calculator, I think I just write the answer for you. It will become minus 125 Newton. Okay, that's the resultant force in X component. And what about the resultant force on Y component? I think I write down here. What about the resultant force of Y component? Okay, Y component, look at here. Okay, we have Y component here, 450 Newton here, and we have to times sine 60 degree. 450 times sine 60 degree. Sine 60 degree, sine 60 degree, and it's pointing down. So there's a negative. Be careful, the positive, negative sign. There's a negative, okay, because it's pointing down. Oh, it's pointing down. And here we have 300 Newton pointing down and pointing down. So that's minus 300. And here is the 700 and the cosine 30 degree. 700 cosine 30 degree. And also pointing down, so it's a negative. So I think that's all. And here we have the external moment acting on this beam, but we're just right now we just calculate resultant force. So we can temporarily ignore the moment, this external moment here. Okay, so you add this together. What's the answer? I think the answer should be minus 1295.93 Newton. Okay, so before simplification, we have Frx equal to minus 125 Newton, and we have Y resultant force on Y component is minus 1295.93 Newton. Okay, that's the before simplification. We have the resultant force. Okay, the next thing is we also have to calculate the moment before simplification. Okay, the moment before simplification. So I just get rid of this. Okay, so if you want to take a note, just rewind and erase this. Okay, so for this simplification problem, resultant force calculation. Okay, yeah, simplification problem, we are calculating resultant force. Before simplification, we also have to calculate the resultant moment before the simplification. Okay, for the resultant moment, yeah, before simplification, what's the resultant moment? Okay. Okay, and because these two problems, we have different reference points, so we have to calculate the MA and MB. MA and MB before simplification. What's MA and MB? That means the total moment of the system, and one is the reference point at A, the other reference point at B. Okay, let's start with okay, simplify this problem. Okay, MA, let's see, A as a reference point. A is a reference point. And so let's see which force will create a moment with respect to A. Okay, so and this force, 400 Newton force, only the vertical component will create a moment with respect to A. Okay, because the horizontal one here, because it acting at this point, is the horizontal one is here, vertical one is here. So this vertical force will create a moment with respect back to A. And the horizontal one, yeah, the lever arm, I think it didn't give any information of this distance. Okay, so that means this distance very small, and we can just assume the moment by this force created by this horizontal force is almost very close to zero. I think in previous example I mentioned this point. Okay, because yeah, the lever arm for this horizontal force is very small, so and didn't give us any information about the distance here. So I think that's you don't have to calculate a moment from this horizontal force. So we only have considered the moment from this vertical force. And here is his lever arm is 2. So it's 450 times the vertical is sine 60 degree. 450 and times sine 60 degree. Sine 60 degree, and it's point down and reference point here. So you create a clockwise rotation. So it will be a negative, and lever arm is 2. Okay, and this force 300 point down here. Okay, and its lever arm is 2 plus 4, and it will create a clockwise rotation. So minus 300 times is 2 plus 4 is 6. And the final is the vertical force here is also create a moment with respect to A. And the vertical force, okay, because it acting at this point, so naturally the vertical force is here, okay? And the horizontal force is here. And horizontal force just the same reason as this force, because the lever arm with respect to A is so small and it didn't give us any information about this distance. So we just can ignore it, okay? And we only consider the vertical component here. And the vertical component is like 700 and the times and cosine 30 degree. And its point down reference point is here, so it also create a clockwise rotation, so it's negative, and its lever arm is 2 plus 4 plus 3, 2 plus 4 plus 3. And finally we have 100, we have external moment here, so it's clockwise, so we have to add in our equation. So that's the total moment of the system, okay? Total moment of the system, and the reference point is A. So I think this answer should be, let me check my notes. I think I check my calculation detail. So this is correct. So this is also correct, and it's correct. So I think the final total moment will be minus 9535.38 Newton times the meter. Okay, that's a total moment before simplification. And yeah, because in order to answer the 3.93, we also have to calculate the moment with respect to B. Okay, so right now the B is a reference point. So right now the reference point becomes here. Reference point becomes here. Okay, let's start with do the similar calculation again. Okay, I think I write a calculation here. MB. Okay, MB. Okay, let's start with an MB. MB calculation equals. Okay, let's start with MB. But right now, reference point is B, so we don't have to consider the moment created by this force. Yeah, because this force or this just acting on the reference point, so there's a moment. Okay, no lever arm. So we have to consider this force and this force and this force and this force, and we only consider the vertical component, because the horizontal component, I think it won't create any moment with respect to D as well, because I think the lever arm is so small, and the lever arm and the problem didn't give us any lever arm at this distance. Okay, so we don't have to consider that. So we're going to consider vertical moment only. And the vertical moment, so be careful. So this is 450 and the times sine 60 degree. And it's point down here and the reference point here, so it will generate a counterclockwise rotation, so it will become a positive. Okay, so this is positive. And lever arm, be careful, lever arm is become like, lever arm will be here, so it's 4 meter. So it's 4 meter and it's positive, and because counterclockwise rotation, so it's positive. And right now here is 700. 700 vertical component is just cosine 30 degree, and because force is here and the reference point is here, so it will create a clockwise rotation. Also clockwise rotation, so it will become negative, and lever arm is here 3. Okay, and finally we have this external moment 1500. Okay, and it's clockwise. Yeah, and so it's minus 1500 Newton per meter. So this is the result of the total moment of this system before simplification. And let me check my the equation. Did I write it right? Yeah, it's right. So the answer is minus 1759.81 Newton times the meter. So we got all the information before simplification, resultant force and the resultant moment. Okay, so right now, So let's see. Okay, the resultant force, resultant moment. So let me write down the information. Okay, so the total moment of the system is minus 9535.9535.38, and moment from B is minus 1759.81 Newton decimal meter. Okay, that's the information before simplification. Okay, so right now we are to start to answer the problem. Determine the resultant position of resultant force. And let's start from the A. Start from A. For this simplification, okay, simplification problem, okay, we already know the resultant force. And next thing we want to know, where is the position of the resultant force? Okay, so we think we can ignore this. Okay, let's start from A. Okay, let's start from A. Okay, after simplification, I think it will be like this. Okay, reference point here is A, reference point A. Okay, and then we have resultant force. Okay, what's resultant force? The resultant force is X component is minus 125. Okay, X component minus 125, and Y component is minus 1295.93. Okay. And so the resultant force will look like this. Okay, but I have to say I didn't draw this picture in the right scale. So okay, just forget. Okay, just it's not in the right scale because it's 1 to 10, but this doesn't look like real 1 to 10. So just very simple graph. So don't bother. So don't ask me to draw a very clear picture. So here, okay, since it is a resultant force, okay, and we want to know what is distance because reference point is at A, so we can set the origin at here, okay, and then we say the origin is at here, so we don't know position of resultant force, so we just set its X. So we have to find X because we already have the resultant. We only got a resultant force, okay. And okay, for a simplification, the very important concept is before simplification, after simplification, your total moment must be the same. Okay, so the total moment before simplification, if we're using A as reference point, the before simplification is minus 9535.9535.38. 9535.38. That's before simplification. Okay, but after simplification, we must have the same moment. We must have the same moment. Okay, so after simplification, this is our resultant force. Okay, just that we only consider the vertical component of this force. Okay, we only consider the vertical component of this force. Okay, so sorry, I shouldn't put here. We only have to consider the vertical force because only this force create a moment with respect to A. So it's 1295.93, and it's a lever arm because it's acting at this point. So actually, this force is here and force is here. Okay, actually, the real force is acting here. So lever arm is X. Lever arm is X, and the force point down and reference point here. So it will generate a clockwise rotation. So it will have negative sign over here, and then so that's a very simplified equation. That's before and after simplification. After is the MA, and equal to each other, before after equal to each other, and then okay, you can find the answer is X is equal reference point is A is 7.36 is 7.36 meter. Okay, that means this distance is 7.36. That's for first problem. And the second problem is the reference point become at B. So we draw the same very similar picture again. But now the reference point is become at B. Okay. The reference point, yeah, B is here. Okay, reference B is here. And okay, and then we also can assume like okay, that's our resultant force. Okay, resultant force like its x component is 125 and y component is 1295.93. So that's our resultant force here. And we want to determine the position, how position. Let's assume it's x here. Okay, because right now we reference point is B, so because we really don't know where is what's the position of the resultant force, so we can assume it's at the right hand side or left hand side. We can also, yeah, that's right. We can also assume it's a right hand side or left hand side. Maybe I also can do this assumption. Maybe this resultant force at acting at the left hand side, at the left hand side, not the right hand side of this reference point. But my thought is okay. If we use B as reference point, let's just assume everything is positive. So I just assume it's at the right hand side of reference point. If I finally got the negative value, that means this force is acting at the left hand side. Okay, if my final value x is positive, that means the resultant force really acting at the right hand side. So I just assume this resulting force acting at the right hand side of the reference point, and I said assume the position distance is x. Okay, yeah, just assume everything is positive. That will make the calculation easier. Okay, much easier to understand. Okay, so we follow the same scheme. Okay, yeah, before simplification, okay, our resultant moment with respect to B is minus 1759.81. It's before, and this is MB. And we have to equal to, okay, so only this vertical, because the force is acting really acting here, the vertical force is real acting here. So only this vertical force create a moment and it's point down. Okay, and the reference point is B, so you create a clockwise rotation, so it will become a negative. Okay, so 1295.93, and lever arm is X. So you put everything, and that's the after simplification and add MB. So the X will be it's really positive. It's really positive. The answer is 1.36. Okay, 1.36. That means that our resultant force is really at the right hand side of a reference point. Okay, and the distance 1.36. Okay, so it's positive. So that means it's at the right hand side of reference point. So here, okay, so our resultant force. Okay, here is our resultant force. Okay, our resultant force. Yeah, 1295.93 Newton, and in 92, its position is 7.36 from A. Okay, and at right hand side, and at the 3.93 problem, the position is at its position is 1.36 meter from from B, also at the right hand side. Okay, so that's the simplification problem. Okay, hope you can get more understand of this procedure. Okay, because this really used a lot. Okay, in the mechanics of material calculation. And before you calculate the total moment of the system, don't forget there's a moment here, so you have to add this into your equation. Okay. Okay, so I just start video here and see you in next video. Okay, bye bye.